Okay, so moving on to Unit 4.6 of the WJC A-Level Chemistry. We move on to amines. Now we're going to look at just basic start off with amines. So an amine starts off with the name we give it. So we know that the suffix would be amine. Oh, I really can't spell. Amine. So if it was propanamine, it would look like this. That is propanamine. It's basic. Okay, so you can have a primary amine, a secondary amine, and a tertiary amine, like an alcohol. So primary amine is just your normal R to N HH. Your secondary amine is N to H to R, and your tertiary amine is just N to R to R to R. So this is when you basically just substitute out all of your hydrogens. So you substitute out one hydrogen in this to get your, so from an NH3 we're talking in respect to. So NH3 you've subbed out hydrogen and you replace it with an R. That's where you get your primary amine. And then for a secondary, you've substituted out two hydrogens, so it's two secondary. And on tertiary, you've substituted out all three hydrogens on your ammonia, so that's when you get a tertiary amine. An aromatic amine is the same, where you've just got your normal benzene, and you've got an NH2 attached to it. So that's the basics of what an amine is and kind of what it looks like. So now we're going to look at the formation of an aliphatic amine. So an aliphatic amine is a straight chain amine. So we're going to look at it from a halogen alkane to start off with. So this is the basic. We'll do one of C to Cl. That's our chloroalkane, just a basic one. And to form a aliphatic amine from that, you just use NH3 with a H2O and an ethanol catalyst. Okay. Not catalyst, sorry, solvent. I don't know where I'm getting catalyst from. Solvent. So that is just solvent, H2O and ethanol. Solvent. That's two thingy in. So you've got to heat this reactants with obviously this in excess. And this has got to be done in a sealed tube to stop, because NH3 can be gas, so it will escape as it's heated and refluxed. So this will look something like this. So we're going to do it as a bromoalkane to start off with. So if we do your something like this, which is bromoethane. So bromoethane on our NH3, obviously in our, and then you have your H2O and ethanol catalyst. Hope I've done that right. Sorry, H5. Not with it today. Ethanol catalyst. You're going to form your ethanamine. Oh, I'm really not with it. It's CH2. And HBr. So now HBr is acidic in nature, because as you look at it again, if that's in solution with your water, you can form a H+. So H+ is making that acidic. So this is actually going to react with an ammonia, with the amine, because amines are partially dissociate to form bases or alkalis. So as that's an acid plus base will give you salt. So our HBr and our amine are actually going to form an ammonium bromide salt. Which will look something like this. That's going to be that's actually ethyl ammonium bromide as an example. Okay, so to get rid of this salt, all you have to do is heat it with sodium hydroxide, and this will release the amine. Okay, so in this reaction, if we were to use, instead of excess, up here, go back up here, so if we used excess NH3, if we were actually to use an excess of our halogen alkane, we'd actually get a secondary amine produced. So if we don't want that, So this is because amine can act as a nucleophile, because it will attach. So let me draw it out. I need to draw things up to explain. Because it's got a lone pair. So this thing is a nucleophile. And it's going to attack our C to B R bond. This is how the mechanism will. It's actually going to attack this, and this is what happens. And it's going to happen in nucleophilic substitution. That is the mechanism for this. Okay, so now we're going to look at the formation of an aliphatic amine again. We did this in the last episode of the carboxylic acids and derivatives of the reduction of a nitrile. So of course we're going to use LiAlH4 and ethoxyethane, which is an anhydrous organic solvent. Just an anhydrous solvent. And it's going to happen as well. So this is going to be in terms of 4 H plus is added. So let me draw up reaction. CH3, CH2, C triple bond N plus 4 of that will give CH3, CH2, CH2, NH2. So you can see the carbon chain is actually increased. Which is not meant to. Why did I think of that? Guess we'll never know. So now we can look at the reduction of nitrobenzene as well. So nitrobenzene we made in the aromaticity episodes. So nitrobenzene looks like this. And we can reduce this to produce a phenylamine. So we're going to do this in terms of 6 hydrogens added. To give 2H2Os. So that is why. So we use 2 hydrogens in order to get the NH2, and we use 4 hydrogens to get to the 2H2O, if I confused anyone. So that's the reduction of a phenylamine. Now the reducing agent for this, we actually don't use our usual LiAlH4 or NaBH4. We don't use any of them. Instead, we're going to use tin and concentrated, so conc HCl, heat it and reflux it. But because the reactants and products are flammable, we do this in a boiling water bath to heat to avoid flames. That's like a safety precaution. Okay, so once you've done that, you're going to form C6H5NH3 plus, which we don't want because that doesn't work if you want to look at it that way. In that case, we've got something that looks like this. Nitrogen can form 3 bonds, remember. So it's going to look like that. So we need to cool it and add sodium hydroxide. And this is going to decompose the salt into phenylamine and some of the tin stuff that you don't need to worry about. But this, once you cooled it and you've added sodium hydroxide, you're going to get phenylamine again. So to separate this, you need to do steam distillation. And you'll get a distillate of phenylamine and H2O. So we used a separating funnel on this to get the immiscible phenylamine. So by immiscible, I mean this solution here. Well, no, not a solution, but it doesn't mix with water. So using a separating funnel, we can get this because we'll have two layers once again, organic and non-organic, inorganic substance. Dry it to remove the water, and you redistill it to get phenylamine. So that's the production of an amine from reduction of a nitrobenzene. Now, as we've touched on a bit before, an amine can act as a base. And this is due to the lone pair on the nitrogen. So in terms of our Arrhenius, it is a proton acceptor, or in Lewis, it's a proton donor. Not a proton donor, an electron donor, or a proton acceptor. Now, the proton acceptor is due to it forming a coordinate bond with this N. So we'll get NH2. Well, the R, we've got this lone pair on the nitrogen. Yeah, so we'll have a coordinate bond forming here, and that's how it acts as a base. So shorter chains will react with H2O, and it's going to form this when it reacts with H2O. And OH minus. That's it acting as a base. So this would have been, the reactant of this would have been CH3 and H2 and water. It's an equilibrium, so it's a weak base, but this equilibrium will lie far to the left. Alkyl amines, however, are stronger bases, and this is because the alkyl group pushes the electrons to the nitrogen, making it more delta negative. This is just the electronegativity of that nitrogen. So if we got here, something like that, these will shuttle electrons towards this, and that's going to shuttle towards that, making it even more delta negative. So that's going to really want to pull electron. It's going to really want to give away its electrons. It wants to get a positive proton towards it, making it a stronger base. Phenylamines, however, instead of, this was looking at aliphatics before, phenylamines are actually less basic. And this is because the lone pair actually overlaps with this delocalized pi electron system. We're going to form like that dummy shape again, kind of thing. So the dummy shape with the benzene ring. So that nitrogen is going to become less delta negative. Phenylamine will react with an acid to form a salt. However, that will occur. So it's not so unreactive that it won't react, but it will form a phenyl ammonium salt, or a phenylammonium chloride would be an example of one. So now an amine, so we want to look at the chain length. So the chain length has an effect on the boiling point of an amine. So the greater the chain length, the more the van der Waals forces between the molecules. So there's going to be a higher boiling point. And that's our basic knowledge from AS and maybe even year 11. However, and then a secondary amine, however, is going to have a lower boiling point than a primary. This is due to the less surface contact. So there's going to be less of van der Waals forces between molecules. So let's first of all look at the first point I made, which is the greater chain length. So we're going to have lots long chain length. So this is actually 1, 2, 3, 4, 5. So this is going to be a pent. It's going to H2. So this is going to have lots of van der Waals forces between molecules. If we have more down here, we've got all these van der Waals forces that are going to occur. Van der Waals forces, remember, are weak forces, weak intermolecular forces. So these could be like permanent dipoles, your hydrogen bonding with your nitrogen. Secondary amines, because there's less surface contact. So that'll be an example of a secondary amine. So for this, we're going to have less surface contact with other molecules. So this straight chain molecule, this whole carbon up here isn't going to interact as well. Or if we have more up here, we're going to have less interaction with molecules down there. So that's looking at primary and secondary amines. But that's probably as a comparison. So amines will have a higher boiling point than the corresponding alkane or alkene. So it's something like ethanamine, which looks like this, will have a greater BP than just your normal ethane. Oh, a ruler. Than your normal ethane. Now this is because of this hydrogen bonding we can form. So amines can form hydrogen bonds on that lone pair they have here. So if they have a corresponding amine up here, we can form one towards there with the hydrogen perhaps, and we can, if there's an array of molecules around it. So it won't form it as such with the nitrogen, it'll form it more with the hydrogen. Something like that. However, amines will have a lower, so amines, so if we look at just your normal aliphatic, will have a lower boiling point than your carboxylic acids or your normal hydroxyl groups, so your alcohols. This is due to oxygen having more electronegative than hydrogen. Remember the order, remember. Fluorine is greater than oxygen, which is greater than chlorine, the first three to know. So we can look at this in terms of the acid chlorides, and then we can look at this in terms of amines. Okay. So that's looking at the boiling points. Now we look at the solubility of amines in H2O. So small amines are more soluble. Now we tend to say up to carbon 6 is when they become more insoluble, as your unsaturated chains or your saturated chains. These become very hydrophobic. And for it to be soluble, it needs to be hydro-loving, water-loving, hydrophilic. So as chain length increases, your solubility will decrease. So if we have just a normal methamine, never said that one before, don't like it. Let's have ethanamine. So this is 2 carbons long, so this will be soluble. If we look at the corresponding H2O molecules, this nitrogen here in the lone pair can bond to here, this oxygen can do that, and now this is due to hydrogen bonding. So as we know, hydrogen bonding can occur between hydrogen, oxygen, fluorine, and nitrogen, often. So that's when it's sparingly soluble, is after carbon 6. So greater than 6 carbons, soluble, sparingly soluble, or non-soluble at all. Phenylamine, however, is sparingly soluble, because it's on that carbon 6 cusp, and of course you got the stability of your benzene ring. Okay, so now we'll look at amides. So an N-sub-amide looks a little something like this. You'll have your R group attached to another R group with one O, nitrogen, and then your R groups, so and so. So that's your normal standard for an N-sub-amide. So as we know, amines can act as a nucleophile. These attack the carbons, that delta positive carbon, on a carbonyl, such as in ethanyl chloride. So looking before it, they are acid chloride. So acid chloride and ethanyl chloride looks at this. C H C double bond O Cl. That's our ethanyl chloride. Now if we were to react this with methamine, which is CH3 to NH2, we're going to get produced N-sub or N-methyl ethanamide. So this is going to be CH3 to N to H to C, double bond O to CH3. That is N-methyl ethanamide. So we can get, to derive the name of this, we can see the methyl bit, this comes from the amide. Sorry, not the amide, the amine, sorry. And this bit name will come from the ethanoyl chloride. I was getting confused with the amines, amides, and all that. Ethanoyl chloride. So the second name is going to come from the ethanoyl chloride or acid chloride, and the first name is going to come from the amine. And this N just means it's got an N between it, or an N sub. This means it's got an N within the molecule. This can be done with a phenol too. So it's a bit like your esterification reaction in a way, but it's with our N sub. The reactants for this are just your acid chloride reacted with an amine. So now let's look at the reaction of an amine with nitric 3 acid. Now we might know nitric acid, which is HNO3. This is nitrogen 5. We're going to look at nitric 3. So this is when nitrogen is in oxidation state 3, what we call nitrous acid. So HNO2 is very unstable, so that's what nitrous acid looks like. However, it's unstable, so we need to make this an in situ reaction. Now this is made by reacting NaNO2 with an acid, so HCl. So an aliphatic amine, and a nitrous acid, this produces bubbles of N2, and you'll see a coloured gas. We won't see it, but you'll see kind of that gassy kind of sense. So this is when you see an aliphatic amine, so we'll do something like ethanamine again, seems to be a favourite of mine. Ethanamine plus our nitrous acid. I'm saying it now. This is going to produce ethanol. And then we see our nitrous gas, which are our bubbles. A bit darker. And water. That is the reaction. And you might get some propan-2-ol and propene off, maybe formed as side products, but we won't look at them. So an aromatic amine and now this is the reaction contents for an aromatic amine, and you'll see why in a minute. If we do it between 0 and 10 degrees C, or less than 10 degrees C, the reaction of an aromatic amine, so I mean this, that's horrendous. Aromatic amine, and we react that with nitrous acid again, we get a stable benzene diazonium ion, I can't say it, benzediazonium ion, which is formed. So let me show you this. So if I react this with our NaNO2, because remember it's an in situ reaction, meaning that the reactant we need, the HNO2, is made within the reaction, because this is unstable to have on itself and react because it might be dangerous, and it will just react with anything in its course. So by having it in situ, it will react with just the reactant we want it to. Now this is going to form this, and we'll see this is why this is a very important reaction in a minute. N plus, triple bond, N, Cl minus. Now we'll see this as a problem now, because this nitrogen and this nitrogen have 4 bonds. We know nitrogen can only have 3 bonds, so this is going to become a problem. Hence why we've got the NaCl minus and the N plus. This plus is 1 extra bond than it needs, and this Cl minus, it's a minus. So cold nitrous acid can actually be a test to distinguish between aliphatic and aromatic. So if we do it below 10 degrees C, so reaction below 10 degrees C, and we see bubbles, so I'll put C bubbles, or no bubbles. So if we see bubbles formed, this will be or the reactant that we use to distinguish this is an aliphatic amine. But if we do it below 10 degrees C and we see no bubbles, we can distinguish to be an aromatic amine. And this can be a test between the both of them. However, if then we reheat this aromatic amine, so we reheat above, so heat to greater than 10 degrees C, it will then decompose, and it will decompose into a phenol and an N2 and a HCl. So we'll get our benzene diazonium ion will become a phenol. So if we then heat it on, so heat above 10 degrees C, we're going to form a phenol. Our nitrogen gas, which will be our bubbles, and HCl, bubbles, gas being released. So now we've seen this benzene diazonium ion up here. Let me draw it down again for us. Why is it so? What's the drawing? Benzene diazonium. So I'm going to draw it again. Plus triple bond N Cl minus. So now we're going to do a coupling reaction. So below 10 degrees C, these benzene diazonium ions, they're very reactive. So this is a reactive substance. Now this is due to its instability. We've got this N plus, NCl minus. It just doesn't look very stable. So it will react with phenols or aromatic amines in an alkaline solution. So these compounds will form an N double bond N, which we call an azo group. And we'll have two benzenes together. So let me show you this. So this is our benzene diazonium ion. Let me spell out benzene diazonium. Diazonium. And it's a salt. That's that cheeky little Cl minus. So we're going to react, if you react this with a phenol, that's horrendous. So this pen is just getting lighter and lighter. If we react that with a phenol, in alkaline conditions, NaOH, strong base, alkaline, we're going to form this azo group. So let me show you this now. So this, and what I meant by the two benzene rings together. And this is known as a coupling reaction. That's really... Right, so this is our coupling reaction. So this is going to form this. And this is an important for a number of reasons. And as our side products, we'll have sodium chloride and water. This was one of the very first dyes. So I talked before about a coupling reaction. Now, coupling occurs at opposite or in the last case in the last bond, adjacent. So this OH here is on opposite ends to this azo bond here. So this is known as an azo group. This bit here. Red a bit. This is our azo group. So that's AZO. Azo group. Now these are known as azo dyes. That is what the products of a coupling reaction are, an azo dye. Now azo dyes, as the printed on the tin, they're dyes. So this product here that we have is actually called something, believe it or not. It's called 4-phenyl azo phenyl. Sorry. That's because you've got this phenyl group here, your azo, and your phenol. Now it's called 4 because it's reacted on the fourth one. The fourth one. And this actually has an orangey yellow colour, so it's an orange/yellow dye. And these are important. Now you need to know a number of reactions. So you need to know the reaction of an amine, so a phenylamine with our benzene diazonium, and this will form an aniline yellow kind of colour. And you can also do it with double benzenes, which can be called naphthalenes. Now when you react naphthalene 2-ol with your benzene diazonium ion, and in your hydroxide conditions, you're going to form this 1-phenyl azo naphthalene 2-ol, which is a reddy colour. Now this looks very weird. I'm actually going to draw it out because it's quite cool to look at. Now naphthalene is a double benzene. And as I was talking before with the opposite reactions, this is actually not always the case. As in this reaction, this OH isn't on the opposite to it, and this is due to the naphthalene. And of course, here is our azo dye. See how these aren't on opposites? That's because of this naphthalene. There we go. That is 1-phenyl azo naphthalene 2-ol, and this is red. So you need to know another reaction, and that's to form 4-phenyl azyl phenylamine, but you can do that yourselves. Now, this brings the important bit of chromophores. Now, these are the part of the molecule responsible for its colour. So an azo dichromophore, as we saw before, an azo di has this in it. Now, a simple dye is azobenzene, which is simply where you just stick a benzene ring to each side. That is a very simple dye. And that will have a colour. I don't know the colour, but it will have a colour because of this azo bit. Now, the origin of this colour is because the colour absorbed is not the colour seen. As you may know from the rudimentary physics, that you have a colour spectrum, and usually you see opposite colours. They're complementary colours. So where it may absorb red light, you may see blue, because red and blue are on opposite ends of the spectrum. Or if you see blue, you've actually absorbed red, or if you see red, you've absorbed blue. So you can then link this to the equations from the AS, which is your E equals HF and C equals F lambda. So this is where your energy is equal to Planck's constant times frequency, or your speed of light is equal to your frequency times wavelength. So if you know your energy, you can find your frequency, because H is a constant, Planck's constant. And C, the speed of light, is also a constant, 3 times 10 to the 8. And you need to know also, as a little recap, that frequency is indirectly proportional, to wavelength. So as frequency increases, wavelength decreases, which makes sense if you think about it. If you've got loads of waves, you must have a short wavelength. But then we can say that as frequency increases, energy increases. So frequency is actually directly proportional to energy, which again makes sense. If you've got loads of waves, there's going to be a lot of energy involved in this. So that's it for looking at amines and the chromophores and the colours. And if you look further at colour as well, not in respect to A's or dyes, of course, but if in like D block, you've got different colours, which are also related to their complementary colours. So the colours you may see, due to the excitation of electrons and so forth. So that is it for this part of amines, or this part of the spec of 4.6. I will do some questions.